Is the picture off? No? Oh, yeah, even better, yeah. Look, even better, I don't give you the endpoints, but you can see the endpoints. You know what they are, right? Because this is a two-dimensional vector field. So the right endpoint is 2, 1, and the first endpoint is 0, 1. It's even easier. Wow. Okay, now what's the difference between that one and this one?
So we have a closed.
It's closed. It's closed. It's closed curve. Now, could you grind this one out? Okay, let me ask you this. Can you use the fundamental theorem of line integrals here? No, not unless you can come up with a potential function. But that would mean potential functions only exist if the field is conservative. So I'm willing to bet this field's not conservative. What if it was conservative? If this vector field was conservative, what would the answer be? 0, because the two endpoints would be the same, right? The starting and ending point of this curve would be the same.
Yeah.
And so if you use the fundamental theorem of calculus and you subtracted the value of the potential function at the two endpoints, your two endpoints are the same, so your answer should be 0. I'm willing to bet it's not 0. So this problem is not about going and getting the potential function. This problem is about you realizing that this can be done two different ways and that you should probably go with the way that's easier, which is probably Green's theorem.
Is that
right?
Ex plus?
Yeah, yep.
Okay.
Yep. Green's theorem, which you will have access to, right? And then we have this one here. Oh, by the way, on the test, I will not be putting the numbers, like what section it's from. That will not be happening. That actually I did give on this final, but they didn't have, it wasn't open note. It was not open note. But I think I told them it was coming from your homework. I said, the test is coming directly from your homework. So that was just to prove to them, yes, this was that number 39 from that section. And that was also to help them see that, like, okay, if you knew what was happening in chapter 13, section 6, you know what to do. So you will not be prompted with anything that tells you. I won't be completely horrible. I'm not going to mix the order of things up, okay? All right? But, so everything will be sequential. Okay, how about this one? Find the surface area of the surface. Well, then you just need to know how to calculate a surface area. What is it again? Double integral over, well, it depends, right? Is your surface a function of x and y or not? If it is, then it's the double integral over the domain of that surface. And then, yeah, square root of 1, square root of 1 plus, yeah. So we're talking about surface area, yeah. And if it's not, if the surface is not something that can be written as a function of x and y, like, what did we find? We found the surface area of something really cool. What did we do? We did a sphere of radius r. And we actually proved that. And you can't write that surface as a function of x and y, so we had to use the good old r of uv. I'm just pointing out that, like, we did it where, yes, the domain was on the ground, and we did it where the domain was not in sight. It was in the background. So this one is straightforward, I think, compared to, like, the sphere one. Okay. I do also plan on including pictures. I will include pictures, and I think they'll be in color. So, okay, this one right here. Now we've moved on to flux, right? Find the flux. I give you the field, and I give you the paraboloid. This one's a little confusing with the picture, right? Because it's hard to see it, but the surface we're talking about is this top cap. It's this paraboloid restricted to this domain on the ground. Do you see that? It's hard to see it in black and white, right?
Yeah.
Sorry about that.
What is that?
Yeah.
No, because it's not a solid.
Yeah, so you can't use divergence theorem. You can't use divergence theorem because it does not enclose a solid. If we're talking about just this piece up here. So you've got to grind it out, right?
Is that the one that we refer to the circle?
Yeah, A, B, C, D. In this case, I think we'd be F.
Yeah.
We'd be F because your surface is a function of two variables, x and y, right? And then you could use that formula there. Yeah. Okay, we just did a surface integral. And now we're back to work. Well, that means this has got to be a theorem then, right? Stokes. This looks a lot like the one we just did in class, doesn't it? We got a cylinder and a plane. We've got the curve, right? We've got the curve here. I will be more specific about the orientation, just to make sure there's no confusion. Counterclockwise from the top or something like that. And I'm not going to try and trick you. I'm not going to be like, ha, 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 I said clockwise, not counterclockwise. You know, it's like, do you know what you're doing here? Like, the idea.
One of them you put clockwise.
Did I?
Yeah.
On one of these?
Previously?
Oh, I did? Was it the one for greens? No.
Yeah,
It was for greens. Yeah. Yeah, it's tricky. At least I said it. That just means you need a negative. Your answer, just change the sign.
Yeah.
Use Green's theorem, change the sign of your answer. Okay, so here, what do we do here? We're using which theorem? Stokes', right? So you've got to, yeah, we did one just like that today. I'm not going to go through that. And then here's another one. We're trying to find the flux over a solid that has a boundary curve. Hey, this is div, isn't it? What's the div of this? 3y squared plus 0 plus 3z squared. 3y squared plus 3z squared. And that looks like a polar looking thing, doesn't it? So 3y squared z squared is going to turn to like 3r squared. It'll work out. Yeah. Okay. And that's it. That was the end of the test. So I have not made the test, so I can't tell you like how many problems there are going to be, or I recommend that you just go through these. Of course, you know, if you want the grade for the mini exams, you go through these. And then if I were you, I would just be like, okay, I'm going to go into 13.6. I'm just going to look at a few more problems, you know? Make sure, go back, look in your homework. If you came in late or didn't hear, the exam on Monday is going to be open note, an open note exam. So you can have all your, open note, there's no restriction really. Your homework, your notes you take in class. You're the only one who writes on a tablet, right? Yeah. Yeah, so there's nothing in there you'll need?
No, I could just print it out.
I do
Okay.
my homework on the tablet too.
Yeah, that's what
You do? Okay. So if you have a tablet, the only thing I'm going to ask is that you sit somewhere where I can just kind of make sure that you're just looking at your tablet and you're not like on Wolfram or something.
So it being open note, could this mean that the problems are significantly harder?
I'm not going to try and make this a harder test. I'm just probably not going to pick problems from our textbook.
Okay.
Yeah, I'm going to take problems from somewhere else. That way, you know,
Did you say open homework or no open?
open homework. Yeah, yeah. You base this is the you're at the finish line. Okay, this to me is just, if you struggle with this test, it's because you don't have resources or there's a big disconnect with everything. All right. Yes.
Can we use a handout to do this?
Yep. Everything. Yeah. Yep. Everything you have. So the more stuff you have, what I don't want you to do is go print out someone else's, you know, like, no, this should be your stuff.
Yeah.
This shouldn't be like y'all get together and figure out which of you has the best notes and make copies of all those notes. You know what I mean? Like, this should be your stuff, no one else's stuff. Yeah. So I'm really looking at this final as being kind of like, hey, look, y'all made it this far, right? Like, you've come to the end of this class. Like, I remember as a Cal 3 student myself, it's a lot of information. you know, and it would be, it's very easy for any professor to walk in here in a calc. You're good.